evening, everybody. It's Friday, and I'm here to take up some of your precious Friday time with another presentation from George Hnatiuk. This time it's titled Misconceptions and Missed Points. Now that's because he wants to address some of the points that were raised in the chat. He feels that he needs to clarify some of the positions and some of the tests that he did, and talk a little bit more about some other stuff. And also he's happy to open the panel up for a member of the panel. And this is going to sound terrible for Spurs, because I just mentioned Spurs chemo to George and he said, could you bring in Spurs as a last resort? So if there's nobody else, however, I mean, right at the hand, he was happy for right at the hand to perhaps join, and then Spurs maybe at the very end. But anyway, George, are you there?
I am here, Ranty.
Good.
Just a moment, please. Yeah, Spurs, I have nothing against you personally, but I've seen that you're totally disrupting hangouts and stuff with your air pressure nonsense. And I'll be happy to talk to you about it sometime later, but I don't want to do it first off in the show here. I want to answer other people's questions before getting to you, but I will get to you. We'll kind of let you come in once some of the other participants have had their questions answered. So anyway, yes, Randy, thank you. Some of the misconception I noticed, I wasn't available.
Let me transition you across. 1 second. 1 second. Okay. There we go.
Okay.
The screen is yours. Away you go.
Okay. Yes. I wasn't available the day after the last show I did with you, Ranty, and I reviewed the show after I got home later that day. This was a show that you had with Rumpus and Dean and a few others on there. And I noticed that there was some discussion as to what I had done in this demonstration. And so I'm going to talk a little bit more about that and then recap. I'm first going to recap a little bit about the gas law and gas pressures, and then get into that demo to kind of clarify things. Now, remember from last time we were talking about the gas law, that pressure times volume is equal to nRT. Last time I intermixed the small n and the big N. The convention, it really didn't affect the presentation at all. It's just a nomenclature issue, but small n is usually used to designate the number of moles of gas rather than big N. So I'm going to go ahead with that. And that n, little n, is equal to the number of gas molecules divided by big Na, which is Avogadro's number. Na is 6.02 times 10 to the 23rd. It's just a number, like dozens or whatever. It represents Na. Avogadro's number represents this number of items. So in this case, we're talking about gas molecules. So if we take the number of gas molecules, divide by this number, this is what we call the number of moles. Mole is a designator for this number. So rather than having these large numbers in our equations, we simplify by just talking about moles. 1 mole of gas is this many molecules. 2 moles of gas is twice this number of molecules, and so forth. So that's what the little n represents, is the number of moles of gas. And when we do that, the cap R, which is called the gas constant, comes out to 8.20574 times 10 to the minus 2, or writing without scientific notation, it's 0.0820574. That is the number R. T, remember, is in Kelvin, not centigrade, but Kelvin. Absolute zero is at minus 273.15 degrees centigrade. This is called 0 Kelvin. So at room temperature, or at freezing, at 0 centigrade, that is a plus 273.15 Kelvin. So basically what it is the temperature scale. If we're sitting here at freezing of water, the freezing point of water, this is 0 centigrade, or 273.15 Kelvin. And way down here at absolute zero, this is minus 273.15 degrees centigrade, or what we call 0 Kelvin. So it's kind of flipped. The graduations on the Kelvin scale are exactly the same as on the centigrade scale. So if you want to find a temperature, say at 20 degrees Celsius, which is 68 Fahrenheit, then that would be 293.15 Kelvin. You just add degrees centigrade to 273.15 to get what it is in Kelvin. So that's the important thing. In gas law, T has to be expressed in absolute temperature, not degrees centigrade or Fahrenheit. It has to be on the Kelvin scale. And then pressure is given in pascals. The metric unit, and volume is given in cubic meters. So that's basically how the gas law is. And the interesting thing about the gases, which still blows me away, is the fact that it doesn't matter what kind of mixture you have of gases or how large the gas molecules are, the same number of moles of gas, the same number of gas molecules occupy the same volume. It doesn't matter how large the gas molecules are or what kind of a mixture of gases that you have. It's really quite an amazing thing. And it turns out what we call at standard temperature and pressure, this is used in engineering and science. And what this means is standard pressure is 1 atmosphere. And that has a very specific definition. 1 atmosphere is equal to 101,325 pascals and is, in the English scale, 14.696 psi. That's 1 atmosphere. That's the definition of 1 atmosphere. It's also equal to, if you like dealing in bars, there's all kinds of different units that we use for expressing pressure. And this is in millibars. 113.25 millibars is 1 atmosphere. So these are in the different types of pressure measurements. We also have, like, millimeters of mercury or inches of mercury. I'll get into that in a little bit later. But the important thing is in 1982, some of the definitions were changed. Prior to 1982, the temperature was always at 0 centigrade, or 273.15 Kelvin. This is when we're measuring things, we do at 0 centigrade and at what we call standard pressure. Well, prior to 1982, a standard pressure was 1 atmosphere. But since 1982, STP means the temperature is the same. We keep it at 0 degrees centigrade, but the pressure rather than being 1 atmosphere, is exactly 100,000 pascals or 100 kilopascals. So in reading the literature or whatever, or old textbooks, you go to old chemistry books and stuff, they're assuming that the pressure on standard temperature and pressure is 1 atmosphere, whereas in the later textbooks, there's a slight difference. There's about a 1.3% difference in what's called the standard pressure. And then in standards labs, we also have things called the normal temperature and pressure, where the temperature is at 20 degrees centigrade and 1 atmosphere. And that's used in standards labs a lot. Now let's look at this. So what I was showing last time is I had this little demo here, this happy face balloon. This is a old helium balloon that I deflated and inserted a tube so I could blow it up. And what I basically have here is this is a Mylar balloon, and there's a straw that's going into the balloon, and the straw has a T. And then on the end of the T, I have one of these little party favors that if you blow into, it goes out. Well, I measured, and it turns out that with the party favor that I have on here will go out when there is on the order of 0.05 psi is when it will extend out, when the pressure inside there is that low. So what I have now is, say we have this party favor sitting here. This is our pressure indicator. And then I'm going to inject gas molecules by blowing in on this end of the straw into the balloon. Well, what I said last time is what's happening. If you look at this, it's, here's our balloon. And what's going to happen is we're going to put gas molecules in. We're going to increase M. And then we have our indicator here. And initially, the balloon was deflated. Just put a little weight on it and let this deflate a little bit. And what the claim was is that if we look at, as I increase N, the gas molecules, what is going to happen to the pressure inside the balloon? Well, you can see that all along here, the pressure is going to be constant. Whatever pressure we have is all going to be along here, going to be at the same pressure. It's at any given point in time. So what I had said is that we're holding temperature constant. This is a gas constant. That never changes. So this isn't changing. So what we're doing is we're increasing N. So if this is held constant, N is going up, then this product here has to go up. Well, how do we separate pressure and volume in this case? That product goes up as the amount of gas goes in there. Well, what's happening here is initially, without any introduction of additional gas, here this thing is sitting, okay? It's fairly flat. So, and this is open to the atmosphere. So atmospheric pressure here is going to be the same. We're going to have 1 atmosphere of pressure in here. Maybe a little bit higher because there's the weight of the balloon. I wasn't talking about this. I was just trying to talk about the net effect of what's going on. Now, if we say, let's start out here at 1 atmosphere. 1 atmosphere of pressure with it open to the ambient just as it is. So the pressure in the balloon is going to be basically essentially at 1 atmosphere. Maybe it's slightly up above it, because what's really happening is you have some weight on the top side of this balloon. This balloon, I measured it, it's about 2 grams, the total mass, the gram weight of the balloon. So maybe about a half of it pushing down is 1 gram. And that's over this surface area here, which is, you know, almost a cubic foot, or not a cubic foot, but a square foot here. So the pressure is going to be extremely small. If you look at cubic meters or square meters to square feet, and the gram, 1 gram is basically a gram. There's 28.35 grams per ounce. So this is about 1/30th of an ounce. And there's 16 ounces per pound. So this is basically 1/30th times 1/16th of a pound of weight pushing down. So we're looking at 1 over 480, 80th of a pound. Very, very little. And say the area here, let's just say, is a square foot. So what we're looking at is about 1/500th of a pound per square foot. If you want to get it to square inches, a square foot is 144 square inches. So we divide even again by 100 to get it in terms of square inches. So we're looking at basically 1 over 50,000th of a pound per square inch. So the amount of pressure increase due to the bag pushing down on the air in there is negligible. So I neglected it. I didn't talk about this because we're talking about, you know, 1/50,000th of a pound per square inch additional pressure just due to the weight of the bag pushing down on the air. So it's negligible. But if you really wanted to get nitpicky and talk about it, yeah, with this thing sitting here like this, the pressure isn't going to be right at 1 atmosphere, but it's just going to be a little bit above it. Okay. Now, as I blow into this thing, whoop, got to go slow. If I inflate this, now if I stop here, what's happening? Okay, it's partially inflated now. So what's going on is the bag now has partially inflated. And I've stopped. So it's equalized. It's still essentially 1 atmosphere of pressure in here, but a little bit higher because of the weight of the bag pushing down on the air. So still, as I'm increasing N, the pressure is going to be essentially the same as atmospheric pressure. What will happen every time I take a little bit of puff, the bag's going to move up. Well, what's that telling us? Well, nothing moves if the forces, net forces, balance out. So what's happening as the bag just sits here like this, we have atmospheric pressure pushing everywhere to collapse the bag, and then we also have atmospheric pressure inside pushing out. So the bag doesn't move. The forces equalize. They balance out. So as I'm sitting here, the bag is just sitting static with equal pressures on the inside and outside. But the instant I start increasing, what is happening here, if you were to take and expand this out, every time I take a breath or a puff of air in there, the pressure is going to increase to expand the bag but then it's going to drop back down as it equalizes to atmospheric pressure. So every puff I take, it's going to expand the bag a little bit more and a little bit more until I've fully expanded the bag. Now we're getting close. What's going to happen the instant the bag totally inflates? Now it's very close. The wrinkles are starting to go out. There. And if I release it, the pressure goes back down to atmospheric pressure. Then when I increase it, the pressure starts going up. And as if I kept pumping more and more gas molecules in, the bag will be fully inflated. This isn't going to expand much because it's mylar. And the volume is going to stay essentially constant. So what's happening? In this area, the pressure is remaining essentially constant at atmospheric pressure. So as I increase the number of gas molecules going into the bag, the volume is going to increase because the pressure is essentially remaining constant at atmospheric pressure. Then, once the bag is fully expanded, the volume can no longer expand anymore. So this remains fixed. So what's going to happen? The pressure will go up because the volume now has reached its maximum. So any more gas molecules that I introduce is going to increase the pressure. So what will happen is the pressure will start going up. So that's what I was trying to illustrate on this. You can get down to the nitty gritty is what's happening. You know, every time you take a puff, the bag's got to expand a little bit. So the pressure has to increase inside a bit to expand the bag. But then once you relax, the pressure is going to go and equalize to the atmospheric pressure. And this is the same sort of thing. I noticed people were in that day after on Renke's Hangout, we're talking about a tire. And the same sort of thing will happen to a tire, except that the tire tends to be a much heavier material. You took like a bicycle inner tube. This is what I was talking about when I meant tire. Might have been a poor choice of words. What I meant is the rubber inner tube that you put inside like a car tire that needs repair. If you punctured the sidewall of a tubeless tire, you put a tube in, or you put a tube into a bicycle. Is you have this bicycle tire, say, sitting like this, and then you have a valve in which to introduce gas pressure or gas molecules. Well, if this thing is initially sitting flat, you know, where you have the valve, this is the same situation as what we have with the bag here. If the valve is open, the air pressure on the inside of this inner tube is going to be at 1 atmosphere, pushing everywhere outward on the tube, and then you have the outside pressure pushing everywhere to collapse the tube, and these two are in equilibrium. They balance out, so the tube just sits there. It doesn't move. But now you put a compressor on here and start pumping in gas molecules, this will start expanding, which means that now the pressure in here had to increase a little bit in order to expand this. And you also have the weight of that material pushing down, like I just went through, that the contribution to the increase of air pressure just due to the weight of that is negligible compared to the pressure that you're putting in to expand the material. So what's going to happen, it's going to blow up, start getting bigger and bigger. And then once it reaches the point where the rubber has to start actually expanding, then we're reaching that point again. Initially, we have 1 atmosphere. It's essentially remaining at 1 atmosphere. And then once that tube starts getting puffed up to where there aren't any more wrinkles or folds in it, then as you increase the pressure, we have a little different situation than we had with the Mylar balloon. With the Mylar balloon, the volume remained fixed as we introduced pressure once we got to its maximum size. So the volume isn't going to increase beyond this on the Mylar balloon. However, with a rubber inner tube for a tire, it is. It can expand. So the volume doesn't remain fixed. So both the pressure and the volume increase together on an inner tube for a bicycle. The material starts expanding, and that material resists additional air pressure. So the volume is going to go up in some manner, and the pressure will go up in some manner together. It's going to be a nonlinear type of relationship because we don't know how that tire, that inner tube, that rubber inner tube is really going to expand and create a resistive force as you're inflating that tube with gas pressure. And so that's the difference, is the Mylar balloon reaches a maximum size, then the pressure increases. Whereas with the inner tube, both the pressure and the volume, once you reach its maximum or reach the point where it's going to start stretching, the Mylar balloon would go something like this, let's say, whereas with this stretching tube, it won't follow that because this is for a fixed volume, so it's going to be a little more complicated. It's probably the pressure won't go up quite as fast because the volume is also increasing and reducing the pressure as the volume goes up. But ultimately, as you introduce more and more gas molecules, the pressure will increase because the pressure will be, the forces on the inner walls of that tube will be greater than the outside atmospheric pressure and the stretching force of that tube.
So George, because I know that you actually specifically asked me to ask you a couple of questions during this presentation. So one thing that stuck out for me last time was the force field that you mentioned. So you made a claim that the force field was what's keeping the gas molecules in to keep pressure against
we can get to
the vacuum of space.
Get to the Earth's sure, we can get to the Earth's atmosphere. I mean, are we done with this then? Pretty much.
Well, I think you've made your point. Yeah, I think you've made your point.
Okay, so you're satisfied with that?
Yeah, you've definitely made your point.
Okay. Well, let's talk about the Earth's atmosphere then. All right. Now, let me get a few things arranged here.
And what I'll do in a minute is I'll bring right the hand in around about 10 minutes, if that's okay.
Sure.
Yeah.
Sure.
Okay.
Okay. Now, let's say we have the surface of the Earth sitting here, and the gas molecules are denser near the surface of the Earth, and as you go up, they get thinner and thinner. So basically what we have, what causes the pressure on the surface of the Earth is the weight of the gas pushing down on you. If you were to take a column, say 1 inch, 1 square inch in cross-sectional area, and went from the surface of the Earth out to space, then the weight of that gas, if you were to put a scale here, would be 14.7 pounds. That was the weight of all the gas in that tube. That's 1 square inch tube will weigh 14.7 pounds. So the weight will be 144 times larger than that. So if I,
it's just starting to buffer, apparently. We're starting to get a bit of buffering. Let's see if I can't change a few things. Just bear with me.
Okay.
We're still streaming for sure, so I'm just making sure that we're not lost anything.
Okay.
Right, let's see if that works. Just one sec.
No problem.
Right, do you want to give that a try, see if that works?
Okay. Are we doing okay now?
Looks like it's back up and running yet.
Okay, just let me know when it's running.
So, yeah, but is this about the force field that we're looking at then, here, George?
Pardon?
Is this to do with the force field?
Yeah, we'll be getting there. Yep. Okay, now I redrew. Here we have the surface of the Earth. We have air molecules. The density, it's most dense near the surface of the Earth, and the density decreases as you go up in height, and the pressure also decreases as you go up in height because the weight of the air above you is less the higher you go up. If I'm sitting here on the surface of the Earth, I have all this column of air pushing down on me, whereas if I go up in altitude, I only have this amount of air pushing down on me. So the weight of the air that pushes down on the rest of the air beneath it is what causes the pressure. Now, this equation here gives you a very good relationship on the relationship to pressure and height. If you put your height, let's say here, your height in meters, then the pressure, atmospheric pressure is 101,325 pascals. That's that number there. And so this complicated equation, it's very nonlinear. It gives you up to about 44,000 meters, a very accurate value for the pressure that you will read versus height in meters. So if any of you are interested, this is a sort of the relationship between height and pressure. It's not linear. As you go up in height, the pressure changes not in a linear fashion with height. What I mean by that, if I double my height, the pressure isn't going to 1/2, or if I go up a factor of 8 on height, my pressure is not going to decrease by 1/8. It's going to decrease more according to this particular equation. It's a non-linear sort of effect. If we look at pressure, say 1 atmosphere versus height, we start out at the surface of the Earth, and rather than being a linear decrease like that, the pressure actually goes way, kind of something like that, in a non-linear fashion. Now, why is that? Well, it has to do with the weight of the air molecules. And that's where this, what you're talking about, Randy, this what I mentioned about force field is I come to this through my training in electromagnetics, and many of you are familiar with electrostatics and magnetostatics. You have a bar magnet, you have a magnetic field around it, or if you have a static charge build up someplace, there's an electric field about it. There's a very analogous one-to-one relationship between the relationships having to do with mass and those having to do with charge. For example, if I take, say, if I have a positive charge and I bring a test charge in from infinity, it takes work to move against. There's an electric field. We're talking about an electric field that emanates from this charge outward.
When you say you bring something in from infinity, what do you mean by
Yeah.
that?
Means you go way, way out in space with a test charge, and you start moving it in towards this charge that's emanating or giving rise to this electric field. An electric field is defined as force per unit charge. And the force equation is charge 1, charge 2, divided by 4 pi epsilon 0 r squared, where if I have two charges and the separation distance between them is r, then the force that's between these two charges is given by this equation. This ought to look familiar to you because this is very similar to when you have a mass. A mass also emanates a force field about it. And the equation that describes this is force equals cap G m1 m2 over r squared. The forms look the same. It's the same type of behavior. If I have a spherical mass or a spherical charge distribution, they both give rise to a field, a force field about them. In this case, the force field, we talk about electric field, is force per unit charge. If we do an analogous thing and talk about force per unit mass, this is acceleration. So around a mass, we have a gravitational force field rather than an electrical force field. There's an acceleration field about this mass. Now, there's been all this controversy about forces, about whether or not gravitational forces are real or not. They're very real. You can describe the effects of gravity on objects or gravitational fields just by using forces. The difference here is many of you will not discount the fact that there is an electric field about an electric charge. The same thing with masses. The only difference here is that Einstein came along and he looked further into the nature of a gravitational field or a gravitational force field and came up with this general theory of relativity of where it can be described using the curvature and bending of space-time, that mass tells space how to bend, and space tells mass how to react to that bending. But we don't have an analogous thing in electromagnetics. We do not have a higher theory going beyond considering that we have charges that create this force field. It might surprise many of you to know that we don't know the nature of these force fields in electrical other than to describe them as being given rise by charges. But we don't know what charge is. It's a name we give to this quantity that creates this force field. The same thing with mass. Mass is a name we give to that creates this acceleration field, except that in gravitational theory, we have yet a higher level in which to look at these things, in which is the bending of space-time. Maybe someday somebody will come along and do what Einstein did for masses due to the electromagnetic theory, due to electrical charges, to tell us what these things really are. We don't know what they are. So if you accept electrostatics and static electricity and the forces that they create, it's the same thing with masses. It's the same equation, same form of equations, the same thing that occurs. So we can think of there being a force field between masses that causes the forces of attraction, just like with charges. I'll show you this right here. There's a big difference between electrostatics and gravity and gravitational theory is in electronics and electrostatics, we have two types of charges, plus and minus. Whereas in the real world, we only have one type of mass. We don't have negative masses. That's the big difference. So if we have, say, a plus charge sitting, minus charge sitting there, and say we have a mass 1 sitting here and a mass 2 sitting here, the forces that are experienced between these two charges, this force field, looks exactly the same as a force field between these two masses. This is an acceleration field. This is an electric field. Force per unit charge. This is force per unit mass. Fields are exactly the same. The configurations are exactly the same because this equation, the force, is it's a product of some constant times, in this case, Q1, Q2 over R squared. And in this case, we'll call this force electric. This is force gravitational. This is some constant K, M1, M2 over R squared, where R is the separation distance between the same form. You can use the same concepts of a force field to describe what's happening between two masses as you can with two charges. Exactly the same form, functional form for the forces. So that's what I meant by force field. It's not a force field like something you find in Star Trek where you create a prison or a barrier. This is a force field between the masses. So if I bring in a test mass, say a little marble, and I kick it out in this direction with some velocity, it's going to follow one of these flux lines for the force field. This is what they call a geodesic in space-time or in Einstein's general relativity. This is a geodesic that it follows. Same thing happens here with charge. If I happen to kick out a positive test charge, it will be attracted to the minus charge over here, and it will follow a flux line, a field line, just like it does for the masses. The analog between them are one-to-one. And the fact that we can use the concept of forces to solve trajectory problems involving the movement of masses works very well. Now, you can argue all you want whether or not there's that force there or not, but the concept of using a force works. It agrees to a high degree of accuracy within parts per million or better in solving these problems, as to consider the gravitational field being a force field, and that you have gravitational forces between objects. Between the Earth, you throw a ball, there's a force of attraction between the ball and the Earth. I can, to a high degree of accuracy, tell you exactly where that ball is going to land by using the force concept. Engineers, physicists use this all the time. Now, the fact that you happen to go to a higher level with this Einstein's general relativity theory to explain where these forces come from is immaterial. We don't have yet an analogous type of thing for the electrostatics, but all of you seem to accept electrostatics and forces.
Can I just introduce you? We've got Right the Hand that's joined the call. Now, the reason I brought Right the Hand in is because this is his thing. He's done quite a lot of videos on gas pressure, etc., and he will be doing a presentation later tonight, funnily enough, on that exact subject on this channel. So you wanted somebody to come in and have a little debate with you, so I've invited right the hand to join. Are you there? Right the hand?
Hello, can you hear me?
Yes, coming through.
Yeah, I
Good.
hear you fine.
Awesome, cool. How's it going, George?
Fine. What's your question?
So let's start like simple. So first, can you try and keep your answers under 15 or 10 seconds? Because any more than that,
Well,
like,
it
it seems
depends
like
on the question. It depends on the
I
question.
keep my,
Some
don't worry, I keep
questions
my questions, they're
cannot be
very
answered
simple.
easily.
Okay, well here, we'll start with the first one. Can you define field for me, please?
Well, I did. A field, in terms of, you mean a force field?
No, just the word field. Don't add anything. I just want how you define field.
Well, it has many different meanings. I could be
in the
facetious
context you're
here and
using
say
it.
it's a place where grass grows.
No, in the context that you used it, can you define it?
A field is the structure of flux lines. Whether you're talking about a magnetic flux, electric flux, or gravitational flux.
Can you define flux lines? Yeah, I'm not laughing. You're using words. I just want to make sure you know what they are. So can you define flux lines? So we have structure, which is the physical conditioning of something. So what is flux?
A line of flux is a illustration, or it's a path that a test charge or a test mass will follow within the field. You have a for example, if I had
hold on, before you go into example, I don't want an example. We're working on definitions. So you said a field is a structure of flux lines, and flux lines are something in the field. Do you see how you're using the same words to describe themselves? So let's simplify it. You have a field. What is your field of? This gravitational field, what makes up the field? Because you can't just have a field. You need a field of something. Like, so we have a field of grass, like you said, or an electromagnetic field. So this gravitational field.
It's a gravitational field.
Okay, what is that made of?
It's flux and fields are mathematical constructs.
The gravitational fields. Oh, so your gravitational field is a mathematical construct.
Yes, it's an acceleration
so it's not real.
field. It's an acceleration.
Okay, wait, hold on. A mathematical construct cannot accelerate mass. Do you agree?
It's a description.
No, I didn't ask that.
Come on, man.
I asked
come on, hey,
hold on, George.
Stop this nonsense.
George, you didn't answer my question. You moved the goalpost, George.
We use mathematics to describe.
I didn't ask that. Can mathematics affect physical matter? I didn't ask that. I asked you, George. George, listen. No, don't get triggered. Don't get. I'm asking. Okay, I'll listen.
Okay. Can you
one at a time, please?
Can you see a magnetic? Can you see a magnetic line of flux?
You're moving the goalpost. We're talking about gravity.
No, I'm not moving the goalpost.
Yes, you are. We're talking gravity. You move it to magnetism. You love to move to something that's real to try and prove gravity. So let's stick to gravity.
Well, I'm trying to give you an illustration.
No. I don't want an illustration. An illustration is not reality. So this is why I'm very adamant of I don't want an illustration. Okay? So we have a field of an illustration, which is, in your terms, a mathematical construct. So my question, don't answer any question but this one. Can a mathematical construct affect matter and make it accelerate?
Why don't you get rid of this idiot?
That's a yes or no. That's a yes or no, George.
No, you have no understanding of what mathematical models are.
Okay, so now I don't understand. There he goes.
So you're telling me. So you're trying to tell me a mathematical construct.
No, I'm not telling you anything. I'm asking you by your own definition.
No, look
yes, and you're not answering. Oh, we got an S. Oh boy, it's triggered. It's triggered again. Randy, I think I might. Can I get the belt? Can I get a triggered belt?
One at a time, please. One at a time. So. Right, okay.
I asked him a very simple question. Can a mathematical construct affect physical matter? No, well, here's the thing. If you're trying to lose me, right, I'm chasing you down. You're giving me this explanation of a gravitational field, and I'm chasing you. And you're trying to lose me right now because I have you. I have you. Okay.
Well, you admit it. Hold on. I'll tell you.
Wait. You're calling me names and you're cursing.
Okay. So George is gonna. So can we give George like a minute or so to do whatever he needs to do to explain this.
Okay,
And
whatever.
then,
Yeah, sure.
And then you can come back and you can say whether you think that
Okay.
he's answered it correctly, or in however way you feel. But just give him the floor for about a minute.
Yeah, he can have the floor.
Whether it be in electromagnetics or gravitational fields, or in the theory of gravitation, we cannot see these fields. We cannot see these flux lines. All we can do is test to see if they're there. There isn't any glasses I can put on to see what a gravitational flux or a electric or a magnetic flux looks like. It's impossible. We can't see them. They're invisible. Okay? So all we can do is test for them. In the case of a mass, if I have a mass like the Earth, and I lift something up and I drop it, I can see how it moves within that force field, within that field. And from that, I can plot out the flux lines by seeing how a test mass behaves as I move it around that mass. The same thing with a charge. If I have a charge, I can't see this electric field. All I can do is measure it by seeing how test charges behave when I bring them in the proximity and let them go and let them move about this field. That's the only way I can see that field.
Okay, right the hand. How do you feel about that?
Okay, so George, would you agree that you don't know the cause of anything? You only see events happening.
Well, I mean, we have a description for causes. I mean, if you get down, I've alluded to this earlier. If you want to keep peeling the onion back and getting down to more fundamental principles, no, we don't know how anything works.
Okay, so hold on.
At a basic fundamental level, all we can do is describe how those things.
So you admit you have no idea how it works, but if you keep dropping a rock or dropping pumice in water, or if you keep witnessing the reactions of physical matter in reality, you can predict how they will react based on doing it before. So basically what you're telling me is that you can drop... Hold on, let me finish. You didn't let me finish. You didn't let me finish, George. Let me finish. So what you're saying is that you can plot how object A will fall, rise, or stay in medium A, and then from that, which is only observations of events happening in reality, so you have observations of events happening in reality, then you plot and quantify those with math, and now you're telling me with that, which is nothing but observations in reality and the quantification of what you see into numbers, you can tell me why it's happening and that it's because space-time is bending. See, I'm going to call bullshit on that one.
Okay, call bullshit on it. Okay.
I am. So do you agree that you cannot prove why a rock falls simply by timing it?
I cannot prove why a rock falls. Well, we have...
No, from timing it. Because you have 9.8 meters per second squared, which is nothing but a rate of descent. So all you're telling me that you can watch something drop at 9.826 meters, blah, 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 and then you can tell me why. So if you see a car drive past you at 55 miles an hour, can you tell me what kind of engine is in there?
Well, of course not.
Okay, so then why do you think you can do that?
How is that relevant?
How
is that relevant?
Because you're telling me that you can do the same thing with an object moving. You're saying you can drop a rock.
Hold on. I'm telling you that.
Yes, you are. You're saying you can drop a rock. Hold on. Let me finish this point. Well, let me finish this point. You're saying you can drop a rock, time it, and then tell me why it falls.
Okay, George.
Because you're saying it's space-time bending.
Yeah, okay, George. Can you answer that, please?
I will, if you guys will let me. We have a description that we have developed through observation. Newton determined, and we have found that works to a very high degree of accuracy.
That's because it comes from the observations in reality. So,
Yes,
of course. Okay, so, but you're not proving the
everything
cause,
we do in
George.
science comes
Yes,
from
George,
observation.
here's the problem.
Hey, will you
When
shut up a minute?
Yeah, when I drop a rock, I know it's going to fall because I've dropped it.
Okay, right the hand. Can you give him 1 minute here, right the hand, just to do his
Sure.
just to do his
I can
thing.
give him 10. He's just going to say the same thing again.
Randy, I'm through with this guy. He won't.
Okay, good. Goodbye, George. I'll take the stage from here. You cursed and called me an idiot, and now you're going to play the victim card.
He's interrupting.
Because you're trapped.
I can't get my answer out. Will you?
You interrupt me. You don't let me say 4 words.
Okay, would you like to have a couple of minutes here, George, to explain your position, or are you actually saying that you're done with speaking with right the hand right now?
Well, I'll explain if you can mute the guy.
There you go, right then. If you just want to give him a couple of minutes just to say what he needs to say, and then you can come back again and challenge him again.
Okay, we'll try it again.
Okay.
All right. Most of science and engineering is observational. And from a collection of observations, we come up with hypotheses and theorems, and we test these things, and we come up with models. A model is something that helps us describe what is happening in the real world. We have these mathematical models. One of the mathematical models we have is that force equals mass times the time derivative of momentum with time, which you recognize as force being mass times acceleration, which is the time derivative, the rate of change of momentum with time. Now, from this mathematical model, I can tell you very precisely how things are going to behave in the real world, how masses are going to behave when I throw a ball up above the Earth at some angle, say 30 degrees, at some initial velocity. I can tell you the parabolic trajectory it's going to take and how far away it will land and the time that it will take. This works very, very well in describing how matter behaves on the Earth or in the universe as a whole, how matter interacts with one another. What more do we need? I don't have to, there is another description going up into general relativity theory where we talk about these things following geodesics, but we don't have to go up to the level of general relativity to solve these problems, just like we don't have to invoke quantum mechanics to solve these types of problems. Though quantum mechanics gives us a description, it's extremely complicated. This is a very simplified set of equations that we have developed over the centuries that help us describe and to solve these particular trajectory problems and problems involving motion in general. We don't need to know what's under the engine to solve these problems and know how they work and know how matter behaves on the Earth.
Okay, right, the hand. Did that answer your question?
No, he did the same. So I got 2 points now. So he just made another question. So I'm going to reiterate because you didn't answer the question. So will you agree that the equations and how trajectory acts don't come from the y of gravity? They come from you throwing something and seeing how it will react. This is a yes or no. Yes or no, George? It's a yes or no, please.
No, I'm not going to give you yes and no answers that can't be answered with yes or no.
But it's an easy question. In order to find out how far a rock will get launched, do you A, do mathematical equations, then launch the rock, then see if the math was right, or do you launch the rock, see how far it went, map it, quantify it, and then you have your equation? Which one comes first, the equation and then the reality? Hold on, George, you interrupted me. Let me finish, please. I know you're excited, and I know you're, but let me finish.
No,
you're interrupting me again.
You just said to answer the question. I'm going to answer your question.
I didn't get the question out, George. I didn't get the question out. And see, you're getting me away from my topic. Here's the question.
Okay, would you like to start over at the hand? Ask your question again.
I just need 10 seconds.
Yeah, sure.
Just 10 seconds. Do the formulas come first and then they're verified in reality, or do we witness an event in reality that gives birth to the formula?
We can do it either way.
Okay.
Once
Wait,
we,
hold
no,
on. Wait,
shut up.
Wait. I'm
No,
gonna.
Okay,
Randy,
let him.
you don't
Okay,
follow
right. I
them,
have to say.
Randy.
Let me ask.
Randy,
That
I'm
was a
gonna
yes or no
stop.
question.
Hey,
It didn't need an
Randy, I'm gonna
explanation.
stop
It
this
didn't need,
unless
George. It
unless
didn't
you
need an
control this
explanation.
guy.
It didn't need you to drone on
Unless
for
you
15
control
minutes.
this guy, I'm gonna
George,
answer.
Okay,
George.
so
I
what's your
want to.
follow-up
Here's the
question?
thing, but this,
Controlling
Randy, hold
Okay,
on.
guys,
This is what he does.
calm down.
Hold on,
Control this
Randy.
guy.
Let me speak. Let me just say this. I ask him something, and then I'm trying to lead him somewhere, and he just drops and then runs for an hour, so I can't catch. Like, I don't need a 30-minute monologue. I asked him, do we have math? Hold, you're interrupting. I asked him, do we have math, then reality, or reality, and then
Randy,
math? And
I'm
then he
done.
wanted to ramble on. He wanted to ramble. He said either. So now I'm going to say, if your answer was either, if you come up with the formulas first, how would you know they are correct?
We test them.
Okay, so would you say that the source of everything is the test in reality? Yes or no?
Well, of course, you need to verify
Okay, so
your
that's
model.
a yes. Okay, so here. So you're saying that everything that you know mathematically and everything comes from events in reality, yet you're trying to tell me the cause, which is mass attracts mass and space-time bending. But you only have the witnessing of events. So you said watching a car go by, you cannot tell what kind of engine is powering it. So again, the same thing I've said 5 times that you've tried to obfuscate on, I'm going to hold you to it. If you can only see and time a rock falling, how are you telling me what is powering the rock falling? For the 4th time.
Okay, right the hand now. Let George answer this.
If he can.
We have a model that we have used. I can't tell you the very.
The model comes from reality.
Now look, okay.
That's where the model comes from.
Are you going to interrupt me, or
Okay,
are you going to let?
Well,
just let him.
The model comes from reality,
Just
George.
let him finish. Just let him finish for a minute or so.
What we do is we make observations, we develop models of the real world to describe what we see. The mathematics follows observations. The mathematical theories follow the observations that have been accumulated. And then what we do, once we've developed a theory, we test it through new observations. First thing we do with our theory is we have to ensure that it explains all the observations that we have to present. Then we can use that model to make predictions. We can change the parameters within that model and then go out in the real world and test the theory to see if it agrees with changes that we've made in the real world to see if it matches up. If it matches up, then we have pretty good confidence that the theory is describing reality. That's what we have here. I can't tell you what the exact nature is of mass. Nobody knows the exact nature of what mass is. We give the name of the stuff in the world the name of mass. And you keep wanting to go down to these fundamental levels that we can't go down. Just
No,
like I
you
said,
do.
We don't know that. No, shut up.
You do. You tell me it's space-time
We
bending.
don't know the nature of mass. We don't know a lot of this stuff down at the fundamental nature. However, the models that we have give us perfectly adequate descriptions of how they're going to interact, how these things interact in the real world.
And I'm going to tell you why your models work perfectly. Because all of the information from your quote-unquote model come from the real world. So if all of your let me finish. Let me finish. But then you don't. But you're not proving anything except that you quantified the real world. You didn't prove space-time bending. You didn't prove mass attracts mass. You didn't prove anything. All you did was go
Who
around.
Said I'm trying to prove? I never said.
You just claim that there's molecules. Okay, you were claiming atoms. You were claiming that there are atoms making up the air. You witnessed a balloon inflate, and you asserted that it's because of more atoms because you've seen it inflate. You're doing exactly what you said you can't do. You're trying to define why.
So, actually,
stop. Let me finish. You interrupted. You can't. You're trying to explain.
You
Let me finish. Let me finish. No,
me...
you go on and on and on. I'm very concise. You're trying to
No, you're
explain
not.
why.
Okay,
Let me
okay,
finish.
right the hand, right
Can
the hand.
I
You've got
explain?
1 minute. You've
Let
got
me
1 minute.
10 seconds.
You've got 1 minute, right the hand. Go ahead.
I'll need 10 seconds. You're trying to explain why the balloon inflates by inflating the balloon, and that's the same as explaining what is powering the car by watching the car drive by.
No,
Yes.
I am telling you. No, I'm describing that the balloon is inflating by the injection
Witnessing
of
it in
gas.
reality.
What? Hey, will you shut up?
Did you witness it in reality?
Hey,
Is that how you're able to describe it?
is
Yes.
this the
So
way
you
it's
witness
gonna
an
be?
event in
You're
yes, it is.
so
So you
inconsiderate.
witness an
Okay, right
event
the
in
hand.
reality.
Hey, Randy, bring someone else on. I'm done
George,
with
you're
this.
such a bitch. Stop whining to
Bring
Randy.
him
Good
on.
Lord.
Bring someone else on. I
Fucking you
can't
bitch
speak
more
with
than
this.
Brenda, and he thinks he's a woman. Can
Right.
you? This is okay. So so let me recap in 10 seconds. He says we get
no,
all
Randy,
of our data
please,
from
Randy,
reality.
get rid of this guy.
Everything we
He's
know
rude.
comes from reality.
I
All
don't
of our
want to talk to
predictions are
someone that's
correct
rude and
because they come
talk
from
over
reality.
I need to
Fine.
intersect,
You won't
right,
give
so-
me a chance to
Okay,
speak.
George. Okay,
Okay.
right. So right the hand will be on later to do another presentation. Thanks for stopping by. Right the hand.
Yeah, thank you, man. All his equations come from reality, and he's trying to prove cause from his equations that come from reality. Have a good one, Randy.
Have a good one. Okay. What I'll try and do, if it's all right with you, George, if you want to take a few minutes, or do you want to actually carry on with anything on your presentation?
No, that's fine.
Okay, so you need to have a little
What do
break.
you want to do?
Sorry?
Oh, what is it you want to do?
No, I wondered if there was anything more on your presentation that you needed to go through.
Yeah. I hope it's not too humid here. I'm just going to show you something. I've got a balloon, and I have some rabbit fur here. Now, if I hold that balloon, I'm pushing on the balloon, right, to hold it up against the board. And once I release my hand, the balloon falls. Okay? I'm pushing again. It's holding it against the wall. I release my hand. Okay. So it's very obvious I have a force that I'm applying to the balloon that's holding against the wall. Now, if I rub this thing against cat fur, this is an effect called the Triboelectric effect. That is transfer of electric charge by friction. And what I'm doing is the rabbit fur, when I rub a plastic rubber type balloon against fur, negative electrons get transferred from the fur to the balloon. Ah, shoot. It's just too humid here. Okay, there we go. Now,
Okay, we get the idea. We get the idea that it's...
Yeah, you get the idea. I mean, everybody's done this at one time. You rub it in your hair, rub it on fur, and it'll stick. Well, what's causing it to stick? There's a force field. There's charge, excess charge on the balloon, that what happens is, looking at a profile view, here we have the wall, and here we have the balloon. And the balloon has an excess of negative charge. And by induction, it causes electrons to move away from the wall and for net positive charge to be on the wall. So there's a force field from the positive charge to the negative charge, an electric force field. And that's what's holding the balloon. Just like we have force fields with gravity. Even though you can't see this field, it's there. There is this force field between positive and negative charge that causes the attraction of the balloon to the wall. And that is counteracting. Without this force field there, this electric force field, the balloon is going to be dropping because of its weight, which is equal to the gravitational acceleration g, which is 9.8 meters per second squared times the mass of the balloon. Well, if the force of attraction due to electrostatics is greater, then it will hold the balloon up. If this force is much greater than the weight on the balloon. So these sorts of things, we can use these sorts of descriptions for gravitation fields and for masses. like I said, the equations are very similar. The force equations, the Coulomb force law and Newton's force law have the same form. So we can use the same types of constructs to describe one just like we do on the other. So go ahead. What is it you wanted?
No, I've just asked if there's any questions in the chat. If there's anything else, because I know that you wanted to revisit this whole topic. I just wanted to make sure that you've covered all the points that you wanted to go back through. You said you was going to also do some fresh stuff that you wanted to talk about. So I wondered if you'd got through all of that.
Well, not really, but we don't have to go through it. It's, all I was going to talk about a little more about the Earth's atmosphere before you brought this rude guy in, but I don't know. Do people have questions regarding the Earth's atmosphere? The fact I think you were asking me about if say we have this spherical Earth and we have an atmosphere around it, what's holding this atmosphere in place? And again, it's this gravitational field that we have a central force that everywhere on the surface or out from the Earth, there's a force of attraction towards the center of mass of the Earth, and all these gas molecules have mass, so we have mass attracting mass, and that's what's holding the gas of the air of the atmosphere about the Earth. You can go into the statistics of it is to describe the motion of air molecules, since there's such a vast number of air molecules. Remember, 1 mole from PV equals nRT. It turns out that at standard temperature and pressure, that 1 mole of gas molecules, which is 6.02 times 10 to the 23rd molecules, a large number, very large number of molecules, that any type of gas molecule having this number occupies a volume of 22.4 liters at standard temperature and pressure. Always, any type of gas. Could be water vapor, could be hydrogen, could be oxygen molecules, nitrogen, carbon dioxide. If you have this amount of molecules of gas at standard temperature and pressure, being 0 degrees centigrade, 1 atmosphere of pressure, it will occupy that amount of volume. All gases occupy that. Now, if you look at the atmosphere of the Earth, about the Earth, we're talking an extremely huge volume. If we say go out to the Kármán line, remember the Kármán line is at 100,000 meters from the surface, or about 62 miles.
Could I ask,
do
you actually know what the prefix atmo means?
What prefix?
Atmo, A-T-M-O, atmo. I'm assuming it's something to do with the atmosphere, but...
Atmo?
Yeah,
A-T-M-O?
Yeah.
No, I have no idea what that is.
Okay.
In relation to.
Right, okay.
So
the Kármán line,
typically ATM is short for atmosphere, meaning 1 atmosphere of pressure, which is 14.7 pounds or 101.325 kilopascals. But if you look at this total volume that surrounds the Earth between the surface and up to the Kármán line, that turns out, if you do the calculations, it's 5.18 times 10 to the 22nd liters. A huge, huge volume. In fact, the volume of the Earth, of the atmosphere that surrounds the Earth from the surface up to the Kármán line, is about the same number, 1/10 of an Avogadro's number. 1/10 of this is 6 times 10 to the 22nd. The amount of liters that's in this volume of the Earth, surrounding the Earth, is almost 1/10 of an Avogadro number worth of liters. Extremely huge. So this equation, you cannot really apply it to the atmosphere as a whole, because what you are assuming is that the volume is very well defined. And it turns out that if you were to look at pressure differentials, let's say take a, down at the surface of the Earth, let's say you have a container. And we know, due to the gravitational forces, that the pressure down at the bottom of the container is going to be a little bit larger than at the top of the container. Well, how much is that? Well, it's almost equal to 0.5 times 10 to the minus third pounds per square inch per foot. So, very, very small differential. So if you, say, have a container 10 feet high, the pressure differential between the bottom and the top is only going to be 10 times this, which would be 5 1/1000ths of a pound per square inch. Very, very tiny. So this equation works very well as long as your volumes are reasonable size. And what's reasonable size? You could probably go up to a height of containers up to several hundred feet before this starts starts deviating from what you actually measure. And of course, it depends upon the resolution. I mean, if you're going to try to say your pressure device is only capable of measuring 0.05 psi differentials, then what this means is that then this you could go up to let's see, one, two, three. You could go up to 100 feet before that pressure gauge would be able to tell the difference in pressure between the top and the bottom. So for any real world containers, this is a very good equation and accurately describes the relationship between a gas temperature, its pressure, and its volume. Now, getting back to this is, so you can't, to the atmosphere as a whole, use this equation for very, very large volumes within the atmosphere, but, you know, reasonable containers, 100 feet high or so, the equation works very, very good. Now, if we were to look at what's called the kinetic theory of gases, is what is happening is you have these gas molecules, say up here in the upper atmosphere. They're getting energy from the sun, UV radiation, and they absorb energy, and they develop what we call kinetic energy. The kinetic energy of something is 1/2 mass times the velocity squared. Now, the more energy that's absorbed for any given mass, this remaining constant for a given mass molecule, the more energy it absorbs, the more kinetic energy it can have, its velocity goes up. But the thing that occurs is there's a limit to how much velocity any gas molecule can attain with the amount of energy that it absorbs. And you can go through the kinetic theory of gases, that the kinetic energy of a gas is also 3/2 times Boltzmann's constant times the temperature in absolute. And if you equate these two, you can get a relationship between the temperature and the velocity of the gas. And there's a thing called the escape velocity. If you look for any mass, any planet or whatever, for something to move with a certain velocity and never ever come back, that it will escape the force of gravity, we call it the escape velocity. And for the Earth, that's about 11. I'm trying to think what that number is for the Earth. Let's see here. Yeah, it's 11.2 kilometers per second. That's the escape velocity of Earth. Now, if anything reaches that velocity, it will escape the Earth and never come back. Well, it turns out that these gas molecules don't ever have to attain the escape velocity because we have a thing called the solar wind that comes from the sun. It's particulate matter that's kind of coming as a wind, and once these molecules get sufficiently high, they get swept away. And the only types of gas molecules that do that are hydrogen and helium. The other molecules are much too massive. The M is too high for them to get a particular velocity at a given temperature. See, if we equate these two, we have 3 halves. Boltzmann's constant times temperature equals 1/2 m velocity squared of the gas molecule. So the velocity squared goes as the temperature. So as we increase the temperature, the velocity will go up as the square root of temperature. If I solve for the velocity is some new constant C1, say, times the square root of temperature. Well, we don't have to attain the escape velocity for these lighter molecules. They get swept away by the solar wind, whereas the much larger molecules like oxygen, nitrogen, carbon dioxide, they're much too heavy to ever attain a high enough velocity to get up into the upper reaches of the atmosphere where they get swept away. So they remain around the Earth in this atmospheric blanket.
Okie dokie. 1 second, I seem to have missed a couple of super chats, so I'm just trying to find, because they've got a question in it apparently. I don't actually see it, so I'll check that in a minute though. Right, 1 second. Right, so we had a question from Rock Farmer who asks, if you take a step back, what in your mind is the main misunderstanding that flat earthers have about science?
Myth about science that flat earthers have?
No, if you took a step back, what in your mind is the main misunderstanding that FE have about science? Oh, hang on.
Hello.
1 second, I'll have to call you back.
And stuff is they don't seem to understand that science is a discipline in which what we do, I'll relate it more towards mechanics and masses and the movement of masses, is that we make observations in the world about us. And we start through observations, we begin to recognize patterns, that things, if we do something in a certain way, we get a certain result, that there's a cause and effect. And as long as we conduct, say, some sort of an experiment or a test in the same manner, we get the same result. And from this collection of observations, we develop a model, a way to describe what is happening. And we try to attach mathematics to it, because with mathematics, we can, once we have a mathematical model, we can, with that mathematical model, change the parameters, change the inputs a little bit, and predict what the new result will be. And then we can go into the lab or out in the real world and conduct an experiment that follows along with those parameter variations and see if what we predicted using that model agrees with what actually happens in reality. And so then we have new observations and a new collection of information And we test these models by, again, making predictions and testing these predictions. And we develop more and more faith in our models once we conduct these tests and we find that they agree with what the models tell us. And so through this whole body of evidence and observations that we make, we develop a high degree of confidence with certain of these models and mathematical descriptions, just like Newton's force law equation, force equals ma. This has been tested, or say force equals ma. This has been tested.
Can I just introduce Nathan Oakley? Nathan Oakley has joined the call.
Sure.
Any chance I can get just a couple of minutes?
Yeah, sure.
Any chance you can present what I've just sent you as a screenshot, please?
Let's have a look, see. Right, okay, yes.
Can you see that, George? It's your presentation from a moment ago.
No, I don't see anything. What are you presenting on? I'm on Skype.
It's on Skype.
It's, I'm presenting it on Skype too, but you might have to watch it.
What?
Can you not say that?
It's okay, I can describe it to him. It's just the diagram.
Just a minute here. I'll see if I can.
It's just the diagram that you drew 2 minutes ago with a picture of Earth next to a picture of a container.
Next to a container.
Yeah, it's okay. The audience can see it. You only drew it 2 minutes ago.
Okay.
Okay, so my question is, the volume would be the amount of space the gas can occupy, correct?
The what?
The volume would be the amount of space that a gas can occupy, correct?
Yes. Yeah.
So on this picture that's hopefully presented to the audience with a picture of Earth, where did you get the volume?
Oh, the volume, I was just assuming that we went as far as the Kármán line, which is 100,000 meters, 100 kilometers, 62 miles. That's sort of taken as the traditional demarcation line between the Earth's atmosphere and vacuum of space. But it's an arbitrary designation because the actual atmosphere just...
No, that's okay. Just ask my question again. Where did you get the volume for that diagram?
Where?
Yeah, I'll just repeat my statement again, George.
All right, yes. Okay, here we have,
George,
what I'm assuming,
George, I had 20 minutes uninterrupted.
No, I'm telling you,
without you being interrupted.
We have two things. We have the radius of the Earth.
George. So, as I conceded when I first asked, the volume would be the amount of space that the gas can occupy. Now, I appreciate that you drawing an arbitrary line that doesn't exist. The actual amount of space that the gas could occupy would be the space that it could occupy. In this case, space.
Sure. Okay.
So where'd you get the volume, George?
Well, I said the volume is out at the Kármán line.
No, George.
Density,
no, George.
Well,
George,
if you'll let me explain, I'll explain it.
No, George, no. The volume is the amount of space that the gas can occupy. And space is a space that the gas can occupy. So
yeah, for all practice,
I know you've had 20 minutes.
Why is it that you guys won't let me speak?
I'm talking, George.
Why is it when you let me speak?
I'm talking, George. George, yeah.
But you're asking a question.
That means shut up, George. That means shut up, old man.
Hang on. Can we get 30 seconds? 30 seconds without speaking.
I'd like 20 minutes, like George has just had, uninterrupted without George interrupting me. I'd like the same 20 minutes George has just had, without him interrupting.
I'll give you 40 seconds, Nath. Go ahead.
Why? I had 25 minutes, and I'm asking him a simple question: where do you get the volume from? Given that the volume is the amount of space that the gas can occupy, and an arbitrary line he draws isn't the amount of space that the gas can occupy. That would be space. It can occupy all of it. Now, this line he's drawn isn't containing anything. It doesn't give him a volume. It's just a made-up idea. A line, a demarcation point, as he put it. An arbitrary point where he says the gas, which is trying to expand in all directions, meets the vacuum. Well, the gas can't just stop when it has more space to occupy, more volume. But George has just decided to arbitrarily assign this line as the amount of volume that the gas can occupy, when in reality, the gas can occupy all of the space. So I'll ask George again. Given that this line doesn't exist and gas can't press on it, where did you get the volume, George?
Okay, now let me explain without interrupting me. As you go up away from the surface of the Earth, the air gets less and less dense. It becomes more rarefied. There's less molecules per unit volume. There's fewer and fewer molecules as you move up. Yes, in principle, the gas could occupy all of space from here
okay.
to
the volume.
be quiet. Be quiet. Be quiet.
Space is the volume.
Look it, I can't proceed if it's not going to let me explain.
Run away
what is
then.
with
Moan
this guy?
and run away while I demolish your argument, George. I'd like to talk and respond. So the spaces George has just conceded.
This doesn't work, Randy.
Yeah, I'm going to leave.
Hey, I'm not given as much time to explain as Nathan gets to us.
I think I should leave. Don't you think? He's not letting me talk. He's not letting me demolish his religion.
No, you won't let me.
Yeah, he's had 20 minutes of interruption. Now he's not letting me talk. He's a fundie.
No, I'm not going to let you
talk. He's a zealot. He's a religious hard. He won't let me talk. I think he should shut up.
Will you please?
Yeah, can you shut up so I can talk, please, George?
So
the space.
Look it, this isn't your show.
Yeah, you're fundy. Yeah, you're going to leave out. You're going to have to leave because you won't let me talk. You won't let me demolish your religion, will you, George? You won't let me talk. You're a fundy. You're a zealot.
Let's get some control. Let's get some control. Some control.
I'd like to talk.
No, I don't want you to talk.
I'd like to talk, George.
You had your say.
Have 20 minutes drive and then keep
talking. No, Nathan, this doesn't work.
Space,
channel.
George has conceded, but won't let me talk to the audience. He's only stating the points. He doesn't want the audience to hear.
I have to intersect.
I'd like to talk uninterrupted by George. I've only been here 5 minutes and he's already interrupted me about 20 times. I'd like to conclude my points, please,
Randy.
I'd like to conclude my point without being interrupted by George. Is that okay?
Okay, if it's a conclusion of your point, that's fine. But Nathan, he was halfway through his demonstration.
That's diatribe. He's had about an hour and a half diatribe.
I had less than 10 seconds to answer Nathan's question before he interrupted me. Now, if you're going to let him do this, Randy, this isn't going to work.
Well, I've taken you both off the call for the time being. No one can hear you, so you both need to. You need to calm down.
Yeah, you will.
This isn't working.
Right.
You can let me talk.
No, I'm not going to let you talk because you wouldn't let me answer the question. You were on there. You spent 2 minutes asking the question.
Okay, right, Nathan.
Okay, the point some more, Fundy. I'm going to talk, George. I'm going to talk uninterrupted, George. You're going to stop, Fundy.
No, I'm not going to stop.
Well, then that's because you're obviously the point. You're a funding. You know this is the demolition of your religion. The space, George, is all of space.
You need to let me answer the question. You interrupted me 10 seconds into my answer. This isn't going to work.
For about an hour and a half, and I'm now talking. You just don't like it because I'm just
so this isn't going to work.
So, Fundy,
can you find someone else?
Don't let me make the point. Someone else that destroys your point. Hey, volume, George. The volume is the amount of space the gas can fill. And in this case, as you've just conceded, I won't let me Willie
Will you let me please and gentlemen? I know where you're going. I know where you're headed with this.
He won't let me make the conclusion.
I'll explain it. Give me a couple of minutes and I'll explain it. I know where you're headed with this.
Okay, yeah, we all know where he's going here, George. So could you try and explain what you was going to explain? You were just saying that the gas, in theory, could fill the space. So
yes, in theory it could, but it won't because of the Earth's gravitational field pulling the molecules back down towards the Earth. I just went through this. The gas molecules up at the outer reaches of the atmosphere have a kinetic energy associated with them. They have a certain velocity, but that velocity for most of the molecules, the heavier molecules of air, do not exceed the escape velocity of Earth. And just the lighter ones, the helium and the hydrogen, have are light enough where they have escape velocities or velocities high enough that get them up past the Kármán line where they can be swept away by the solar wind. The heavier molecules never reach that height. They never get that high because the weight of those molecules is greater than the kinetic energy can push them up into the outer reaches of the atmosphere. So they just hug the Earth closer in. Now, of course, if you go up higher and higher, there are some gas molecules out here, but they're very, very few per cubic meter. You start going out in here, you might only have 100,000 molecules per cubic meter, whereas down on the Earth, you have an Avogadro's number per cubic meter, much larger. You have a cubic meter is 1,000 liters. An Avogadro number of molecules occupies 22.4 liters. So you have about 50 times Na, or 50 times an Avogadro number of molecules per cubic meter. You're talking about 300 times 10 to the 23rd molecules per cubic meter down here at the surface of the Earth, whereas way out here, you're lucky to have 100,000, 10 to the fifth molecules per cubic meter. We're talking, 18 orders of magnitude more molecules per unit volume down here. Sure, their molecules can go way out into space, but the thing is, there's not many of them that ever make it that high to go out into space and to occupy the volume out there. You can occupy the volume of space, but there aren't that many molecules coming from the Earth's atmosphere that get up there to occupy it.
So what about the second law of thermodynamics? Because I've heard that mentioned several times. So can you explain?
There's no violation of second law of thermodynamics. I'll get into that here. Yeah. I'll try to give a simplified explanation on that.
If you could explain why the second law of thermodynamics isn't relevant in this particular instance.
Yes, I will. I'll give you a real quick illustration.
Well, no, you don't have to do it quick. I'd prefer you to go into a bit of detail because it does seem to be a sticky point.
I'm not going to get into detail. I'm going to give you the explanation here. Is the second law of thermodynamics states that in a system that the system tends towards what we call increase in entropy. Entropy being a measure of disorder. Now, that is true in the global sense. However, you can reverse the second law. For example, suppose you have a tray, and in that tray, you have blue and green marbles, okay? And let's say you order them. So you're looking in the tray from top down, you've got blue marbles, and then you've got green marbles. They're all ordered. This is an ordered system. Now, you set that tray, say, on your car or in the living room or something. After a few months, will these balls still be ordered? Probably not. They'll get jumbled around. There'll be a random order of green and blue marbles. So it's tended towards disorder. The entropy has increased in this system. Well, if I input energy into the system, I can reverse the disorder. So if we put energy into the system, I can come along and I can pick up this random order of marbles and reorder them and put them in a nice row. I've inputted energy into the system and I have reversed the entropy. And that is what can happen here also on Earth, is if you have, say, the Earth, and you have the atmosphere of the Earth, and sitting over here, we have the sun putting forth energy. That energy is coming into the Earth, and there are systems within the Earth where this energy is input. It's input into life here on the Earth, to us, to you and I. And we can reverse entropy. We build houses. We take random forests. We cut down the trees. We make lumber. We build houses. We order the system. Because energy inputted from the sun has reversed entropy on the local system because we've inputted energy. We can reverse the entropy on a local system in a local sense. And the same thing can happen with the atmosphere. But overall, the entropy of the system is increasing. If you consider the total energy output of the sun, you have all this energy that's being dissipated into space, and a very, very small part is actually coming from the sun to the earth. This energy coming from the sun to the earth can reverse entropy on the earth, whereas as a whole in the universe, entropy is increasing because when you order something on a local scale, it comes to at the expense of entropy in the big picture. So this whole idea of entropy, the second law being violated, and that is nonsense, because you can reverse entropy on a local level by inputting energy into the system.
Right, okay, so there's just a couple of questions that I want to ask right now, if that's okay with you.
Sure.
Okay, so we had, where's he gone now? Ah, there we go. So, hang on. Why does gas behavior with respect to elastic collision not take into account gravity except when required to create a force field?
Why does gas in an elastic collision?
Why does gas behavior with respect to elastic collision not take into account gravity except when required to create a force field?
Well, the thing is in the kinetic theory of gases, is if you have gas molecules, moving around in all kinds of random directions, and they do come within one another and collide, but that's a different system dynamics than having to deal with gravity. I mean, the gravitational field, or the forces of gravity between individual molecules, is so minute and so overpowered by the kinetic energy that it doesn't enter in. I mean, it's so insignificant. Whenever solving problems in physics, you have to look at what are the major factors that come into play into affecting the result. I mean, if, say, the gravitational forces in this case, since you're dealing with the masses of molecules, the gravitational forces are going to be on the order of probably trillions of times less than the forces of restitution and the inelastic collision type forces that you're going to deal with. I mean, they're just so insignificant. It's just not going to come into play when dealing with the randomness and the kinetic distribution of gases when you're looking at Maxwell's distribution and Boltzmann's equations and this sort of thing. They just don't come into play because it's so insignificant. But when you take the atmosphere as a whole, you have a huge mass of gas. I mean, when you look at the volume that I said out to the Kármán line, where you're about 1/10 the number of an Avogadro's number of liters, that's a massive amount of it's a huge amount of gas and of mass. So there, as a whole, you can use the dynamics of gravity of gravitational forces to describe what is happening. But on an individual molecule level, no, it doesn't come into play because the gravitational forces are so minute between any two molecules. You have other forces, van der Waals forces, that come into play that occur at a very short length when the molecules get close together. You have other attractive forces besides gravity that totally overpowers what what's going on with gravitational attraction.
Okay, so we have a follow-up question from the Adam Meakin again. Let me just get that question. Just everything's freezing up at the minute, as typical. Okay, so do gas molecules go faster down than up after an elastic collision?
Go faster down than up? Yeah, not necessarily. I can't really answer that. That's a little bit out of my field in terms of statistics. I'm starting to look at the Boltzmann and Maxwell statistics having to do with gases, but my guess is that the velocities related to the kinetic energy of molecules is just so great that the randomness predominates, that there is no preferred direction up or down or sideways. It's a total random distribution. And even when they collide, they're not going to necessarily have, my guess is that they're not going to have a preferred direction to go.
Okay, and we did have a question earlier from Quantum Eraser who asks, ask him about closed thermos, and in brackets, open systems.
So do you really want to get into open and closed systems? Well, it depends on your, there's many definitions.
Well, the exact words were closed thermos, open systems.
Yeah. Well, again, it depends upon whether you're talking about open and closed in a thermodynamic sense, or open and closed in an engineering sense, or a chemical sense. Each discipline has some variations on it. Now, the ones that people normally think of that I don't use, I use the engineering definition, but if, say, you have a thermos and you have a hot liquid in here, and let's say it's well insulated. So we have an insulated thermos, and we have this very hot liquid inside. Now, in a thermodynamic sense, and let's say this is totally closed up, okay, so there's no leakage. Now, in a thermodynamic sense, you can't have matter transfer, but you can allow energy transfer. So, since this is closed, say this is a steel vessel, obviously there's no mass transfer. So there's no mass moving in or out. The hot liquid vapor in here stays in here, it doesn't escape or anything. But thermally, eventually you could allow heat to escape, heat energy to escape. And this would be what we would call a thermodynamically open system. Now, if you don't allow any energy or any mass transfer, then we call it an isolated system. And but in an engineering sense, there are definitions of open and closed where you do not allow either energy transfers or mass transfers. So I'm sorry, what I meant is this is a closed system. I didn't mean open. Thermodynamically open or closed means that you can't have mass transfer, but you can have energy transfers. This is closed in the thermodynamic sense. And an open system allows you to have both mass and energy transfers if it's open. That is, if I all of a sudden open the top, we could have some gas molecules escaping, so there's obviously mass transfer occurring, and we can also have heat transferring. So we have both heat and mass transfer. And in a closed system, we cannot have mass transfer, but we can allow heat transfer or energy transfer. That's allowed. And in an isolated system, you can't have heat or mass transferring out. But in an engineering sense, for a closed system, we also require, in an engineering thermodynamic closed system is like, or an engineering closed system is like a thermodynamically isolated system that you can't have mass or energy transfers in or out of the system. We call that closed in an engineering sense, and also they use that definition in chemistry. So it depends upon what discipline you're considering when you want to talk about open and closed, because some require thermodynamics allows this heat transfer out of a closed system, whereas in a lot of other disciplines they do not allow heat transfer out of a closed system, and it's more like a isolated thermodynamic system. So it just depends upon what discipline you want to talk about when you're talking about open and closed.
Okay, well, I think what he's obviously is he's going to be bringing this back to the shape of the Earth, so, and the nature of the Earth. So how would you apply it to that?
What, in a thermodynamic sense?
In the idea that you've drawn a container, how would you apply that to the? I mean, what would be the barrier around the Earth that's stopping the gas molecules leaving? Is that because you mentioned a force field?
Well, there is no. The Earth. No, it depends on the system that you can consider. You're considering is. On the Earth, there are open and closed systems. It depends upon what you're talking about. If you're talking about the Earth as a whole, where you have, say, planet Earth, we would call this, in a strict thermodynamic sense, this is an open system because we can have both mass and energy transfers. We've shot rockets up into space. We've lost that mass. That mass is gone. Mass is transferred out of the Earth. So that right there tells you that it can't be a closed system. Also, we also radiate energy out. We absorb energy from the sun and we radiate it out at nighttime. Energy is lost. So both mass and energy are transferred out into space from the Earth. So this is an open system in that regard. But you can, if you look at other things like the ecosystem of the Earth, like life, the ecosystem, it can pretty much be considered a closed system because you've got it's self-sustaining. So it just depends upon the system that you're looking at. A system, in one sense, can be open. In another sense, it can be closed. It just depends upon what the overall system is and what the subsystems look like.
Okay, so from Pete Shea, he asks, why can't the Earth be flat and stationary?
Well, I'll give you my reason. It's probably not going to satisfy Pete, but if you were to look at Newton's gravitational force law, that if you have two masses, M1, M2, they attract one another, okay, by this force equation. Now, if you have a large collection of mass, like in interstellar space, these nebulas and that, where they're huge, tremendous amounts of gas clouds and matter, is what will happen, and you can easily prove this using calculus, is that, say we have some matter, and they attract one another. What's going to happen? They're going to start coming together and coalesce into a form. Now let's say we have enough particulate matter out here where all of a sudden we're getting, it's collected into this kind of potato shape. Now, the center of mass of this will be such that, let's see here, the center of mass will be skewed over from the center. So any other, say, new matter coming in, it'll get attracted towards the center of mass and start collecting. And what you will find, let's say you happen to have a rectangular shape of matter. The center of mass is going to be here, so any new matter coming in is going to get attracted and attached towards the center of mass. So it's going to start building up here, same thing here, start building up here, and you will find that as you introduce larger and larger collections of matter, that this thing will eventually start forming a sphere. That is the natural low energy state for a collection of matter. Is nature always tries to reduce the amount the energy state of a system. Is it takes energy, say going out from deep space out at infinity, coming in, and the shape that will give you the lowest energy is a sphere. And that's what nature always tends towards, is to get to produce things in a minimum energy state. And that's the best explanation I can give right now without going through the mathematics of it. Is, again, if you happen to have an odd shape of matter and you have more matter coming in, that it will tend to fill these voids and eventually distribute itself into a sphere. It's just a natural state in which a collection of a large amount of matter will coalesce and form that kind of a shape. So it's only natural for planets. Why is it? We look out into space, everything we see is round, right? Stars look round, all the planets look round, all the moons look round. Why would the Earth be an exception?
Well, if you're on a snooker table and you look up, the balls will be round and the snooker table will be flat.
Pardon?
The snooker table bed would be flat and the balls above it would be round. Just because it follows that the balls, it looks like there's the ball shape up there, doesn't necessarily follow that you're living on a ball either. But we had a question from...
Well, no, Ranty, just a minute, Ranty. What you're saying...
This is following on from this point now, but it's from a question from the Adam Meakin, who asked, can you demonstrate what you've just drawn there, or is it just mathematical?
Well, I just did point out to you what that is. You mean demonstrate like in a lab? No, not here on Earth. I would not be able to do that because the Earth's gravitational field totally overpowers anything that you try to do. Now, if you could go out into interstellar space away from the Earth or the Sun or something where you don't have this overpowering gravitational field, yeah, you'd be able to demonstrate it, but you can't do it on Earth. It's like this. Suppose you have a soccer ball, and I tell you to take a canister of talcum powder or cornstarch or whatever and coat the ball. So you take it and you shake it, and you can probably get it pretty well coated around on the surface. Now, suppose we have a fan here, and we turn on the fan. I tell you to do the same thing. Are you going to be able to coat that ball as uniformly as you did without the fan going? The fan has a very strong wind. That's what's happening with the Earth, is you have this very strong gravitational field, so there's no way, if I take a collection of small matter, like marbles or something, and be able to demonstrate that they're going to come together in a sphere, because the Earth's gravitational field far outswamps any forces of attraction between these things. So you have to get out away from the Earth. There isn't any way
Has it ever been
demonstrate
demonstrated?
this on the Earth because of the Earth's gravitational field far over dominates any sort of experiment that you'd be trying to do.
So has it ever been demonstrated? Ever?
Yeah, actually, there was a video on board the ISS where they showed the natural shape of a glob of water. If you pushed out a glob of water, it will eventually come and form a sphere. I could provide you a link to that. I have it stuffed somewhere. It's kind of a cute video. It's where what they did is they blew out some water, so it kind of came out in a glob like that, and then eventually it ended up in a sphere where it all came together into a sphere.
Okie dokie. Right, I think to be fair, there is a lot of questions, but I think you've already given us what 2 hours and more. So, and I've got another show starting soon, so I think we're going to round this one up, George. If there's anything you want to say, I'll give you 5 minutes to have a quick round up. If there's anything you want to go back and talk about, I'll give you the floor for 5 minutes, and then I'll wrap it up.
No, the only thing I have to say here, Ranty, is for the most part I was satisfied with what went on here. But when you bring in people like this, Wright the Hand and Nathan Oakley, that ask something, and then when I attempt to speak, and not more for 10 seconds, they start interrupting me, and then they demand that they have all the time they want. That just doesn't work. So in the future, what I would do, I would ask you to do with other people to be respectful and considerate of your presenters, is to somehow put these kind of guys under control and maybe have everybody muted, and you yourself control how much time they get to speak, and then when they're through speaking, they're muted until the host or the presenter has his chance to respond, because these guys never gave me a chance to respond, and it was very rude.
Okay, well, just to give you a chance to respond, I mean, I know that we've talked about this off air, but would it be possible, if you want to, discuss or quickly go over this Brian Mullen incident? If you don't want to talk about it, that's fine, and if you're happy to talk about it for just a minute...
Okay. I will. You're kind of blindsiding me on this.
You don't have to talk about it.
No, that's okay. No, I will, because it keeps festering. All right. What I would like someone out there to do is get Brian Mullen to come on to a show with me, or even by himself, to explain what went on. Is back in ED 2.0, I had seen some of Mullen's videos, his balls out physics, and I commented to them, and particularly his episode 1 about planes landing on a spinning ball, and then his episode 3, I did a response to his episode 3 on deriving Kepler's law, and where he went off the rails on that one. And so I got a little puzzled. What got my attention is he had in some of his videos claimed that he was a professional engineer. So I'm thinking to myself, how the heck can a professional engineer get so many concepts of physics wrong? So I did a little digging, and he had claimed that he had a professional engineering license out of Florida. So I called up the professional board of engineers and their office, and spoke with the secretary there. I was trying to find information online regarding his licensing status, and she helped me out, navigated me through the website, and I found that indeed Brian Mullen did have a professional engineering license, and it was active, and I let it go at that. I never ever, what you have to keep in mind, these offices of the boards of engineers, professional boards of engineers are made up of professionals in the industry. They have daytime jobs. They tend to be professors and heads of engineering firms, and they get together once a month and address issues that are brought before the board. They don't have offices at the board of engineers that you call up. All you do is your questions get fielded by a secretary, and that's who I spoke to. And I asked her, to help me find, the licensing status of Brian Mullen, and she did, and I was satisfied that he was a licensed professional engineer, and let it go at that. And for some reason, I've somehow been accused of calling up his employer and trying to get him fired and stuff, and nothing could be further from the truth. I've never called up his employer. I've tried contacting Mullen several times, sending him emails, but he's never responded. So a lot of this conjecture going on out there about me trying to get a man fired is just totally false and wrong. I never did, and I'm just kind of rolling with the punches. I mean, I've heard it so much, it just doesn't bother me anymore. It used to bother me, but it doesn't bother me anymore. And what I challenge anyone to go to the Florida website for the Board of Engineers, and their minutes are all public. They're required to have their minutes public. You can go back and look in that time frame to see if Brian Mullen's name ever came up in the minutes, and you will find that it had not been, at least not from me. Now, it's not to say that someone didn't call Mullen's employer. I don't know, but it wasn't me. And so what I would do, I would challenge anyone out there to find any evidence whatsoever to tie me into any difficulties that Mullen may have had. He's never been fired. He still works for this surveying engineering firm in North Carolina, Boone, North Carolina. You can go and check online. I'm trying to remember, it's called like Arity or something like that, an engineering firm that he works for. And he's worked for that firm for years upon years, even before I started inquiring as to his licensing status. So Arity is the company's name. And so he's never been fired, and he's never been disciplined by the board of professional engineers. There's never been any action taken on him. It would be a matter of public record if there was. You can go in and check on the website. And like I said, as I challenge anyone, is what I'd like to do is I'd like to have Brian Mullen come out. He's the only one that knows if anything happened, and if it did, what happened, and who may have caused it. I mean, he's the only one. Stop all this conjecture. It's just conjecture. Nobody knows. Only Brian Mullen knows. I don't know. You don't know. Riley claims.
Yeah, I hate to interrupt here, but am I going?
Yes. Yeah. I'll be
repeating the same nonsense we've heard. So I'm work. Like you said 4, I ain't trying to be a dick, but if when I say I'm gonna do something at 4, it happens at 4 o'clock because that's just the type of person I am. So I'm sitting around here waiting, blah blah blah. So
give me 15.
Okay.
Just saying.
So that's it. Anyway, Randy,
George, you're not saying anything we can't get out of the Google, right? I can Google everything you just told me, and since you can't demonstrate it, what fucking good is it?
Okay, right.
So Randy, anything to do with Brian Mullen, I would hope, I would really like to get onto a hangout with him and have him ask me questions, me ask him questions. But I have a feeling that, he's kind of washed his hands of all this flat earth stuff and the notoriety that he had. But that's just conjecture. That's all we all have. It's just conjecture. We really don't know what happened or why Brian Mullen disappeared out of the flat earth scene. Only he can answer it.
And did you happen to mention to anybody that he was a flat earther or anything, or?
No.
Okay. Right, and so I just have to ask this one last question. I hope it can be a quick answer, though, because we got a super chat from Ali B that asks, if heat cannot transfer in a vacuum, how did the planets dissipate their heat?
If what now?
If if heat cannot transfer in a vacuum, how did the planets dissipate their heat?
It can. There's three types of heat transfer. There's convection, conduction, and radiation. You don't have convection or conduction in space, but you do have radiation. Radiation is a very powerful way of transferring heat. It goes as the fourth power of the temperature. So there's three methods of heat transfer. Just because you don't have material out in space doesn't mean that energy can't be transferred. It's transferred through radiation.
Okie dokie. Well, thanks very much for coming along, George. You were very accommodating yet again, and I appreciate you answering the question about Brian Mullen. I really do, and for handling yourself against Wright the Hand and Nathan Oakley. For taking your time out and actually doing a presentation. I do appreciate that, and I hope you managed to get everything clarified up from the first presentation from the first time around.
Okay, Randy. Yeah, in closing, all I'd say, I'm appealing to Brian Mullen out there. I'm really tired of this nonsense. If you are watching this at all, please tell the flat earthers what happened. If I'm at fault in some way, I'd like to know. I'd apologize to you if I am, but I can't see how I possibly could be, because all I did was inquire into your licensing status, and that was it, and I let it go at that. But only you, Brian Mullen, can tell the flat earthers what really happened. So there it is.
Okie dokie. Right. Well, thanks very much, George. And I'll speak to you probably tomorrow. I'll give you a call about this. I'm just going to set a new show up for Wright the Hand. Okay.
Okay. Cheers. Catch you later. Thanks.
See you later.
I know. Bye, everybody.
Right. So that was George and his presentation. Hope you all liked that, everybody. Unfortunately, I have to wrap this one up rather quickly because I do have another guest waiting to do his presentation. So that will be Wright the Hand, and he's going to be doing his presentation. Hopefully, we'll get it up and running within 10 minutes. So tune in again, and I'll see you all in the next one.